Hello, and welcome to the third part of my series about how we found out how far away the sun is. So, in the first part, we looked at the ancient Greeks. In the second part, we looked at the so-called scientific revolution that told us what was going on in the solar system, but didn't tell us its size. And so, in this case, we're going to look at the great project that measured how far away the sun is. And it did that by looking at transits of Venus. That's times when Venus travels in front of the sun. Sort of partial eclipse of the sun, if you like, by Venus. So, summarize what we knew at this point. After Kepler and Newton had done their work, we had an extremely accurate map of the solar system, which not only told you what all the orbits of the planets were, but how they moved around them. So it was a predictive map. You could tell what the solar system would look like at any point in the future as well. But it didn't have a scale. We don't know how big it was. But we could predict things with great accuracy, but people still wanted to know how far away the sun was. But now we've got this map, measuring the distance to any planet would be sufficient because then we've got the scale. So why look at transits of Venus? Well, people have tried other things. You can try looking at when Mars and Venus get close to a sun. They can try and measure parallax, but not very accurate. You can get to about an arc second, which is pretty good. That's sort of 60 times better than Tycho Brahe was doing. We've got telescopes now, but still not good enough. So, nevertheless, the astronomical unit, which is the distance to the sun, had been narrowed. Well, the average distance to the sun. Of course, everybody knew it varied, and they knew how much it varied, and it got somewhere around 20,000 Earth radii, which is not bad, but they wanted better. So now this prediction business. So in 1716, Edmund Halley, he of the comet fame, predicted that transits of Venus would occur on those two dates, June the 6th, 1761, and June the 3rd, 1769. That's some 50 years in the future, to the nearest day. It's pretty good, isn't it? And he said if we could time those accurately, we could effectively increase our angular resolution to a tenth of an arc second, get a tenfold increase in accuracy of all our measurements. And the international scientific community responded. And then we're going to see how it did that. So let's look at the transit. This is an excerpt from a paper you might like to read, actually. So Venus goes across the face of the sun. It takes about 6 hours, actually. And there are 2 points in particular that are significant that you might try and time. There's this one here where it first hits the edge of the sun, and this one here where it first, as it were, leaves the edge behind, and here where it first hits the far edge, and here where it leaves the whole sun behind. Now, T1 and T4 are pretty clear. T1 in particular is very hard to predict because you can't really see Venus when it's very close to the sun. Right? It's invisible, and you've just got to see when this slight darkening of the rim happens. That's much hard. That's very hard to do. T2 is relatively easy, or so they hoped, because you can see it coming. You can see the shadow on the face of Venus, and you've just got a time where it leaves the edge. And T3 similarly should be fairly easy to do. And that's the theory. And so what's going to happen here is that when you look at somewhere further up on the Earth, further north, you're going to see it lower down the sun, and it's going to take less time to cross the sun. From further south, it'll be further up the sun, and it'll take longer. So that's the timing that you could use to measure essentially this tiny angle here, and therefore work out how far Venus is away. So I think about 120 expeditions were sent all around the world, Northern Hemisphere, Southern Hemisphere. But it was during the Seven Years' War when France and England were at war with one another. So there are stories associated with that. One of them is that Mason and Dixon, you may have heard of them, right? Especially if you're American, because they were the guys who later than this laid out the boundary between Maryland and Pennsylvania, which later became the sort of distinction between the southern states and the northern states, the slave states and the free states. But at this point, they were English gentlemen going off to observe the transit of Venus, except that it was in the middle of the Seven Years' War, and their ship was attacked by the French and damaged, and they limped back to port. And they said, "Oh, not doing that." But actually, they'd already got a contract that said they were going to. So, under threat of prosecution if they failed to do so, they did set off again. And this time, they made it out of the channel anyway, and they were setting off for Sumatra. But they lost so much time they couldn't quite get there. They failed to get there, and so they got only got as far as South Africa, and they observed it from there. But actually, the 1761 one wasn't terribly good. There was sort of bad luck. This is part of it. There's lots of other bad luck around, a lot of bad weather in various places, and they didn't actually get terribly far. But they learnt quite a lot and had another go in 1769. So this is one of the stories. This guy, Guillaume Le Gentil. So he set sail for Pondicherry in 1761, which was then a French possession. But the ship got blown off course, and by the time he got close, the British had taken Pondicherry, so he had to go put back to sea, um, and so he missed the transit. He didn't see it at all. That's bad luck. Um, so he thought, well, never mind. I'm out here in the Southern Seas. I'll wait for the next one in a year's time. So he did various sort of scientific work, mapping and what have you. By this time, Pondicherry was French again, so he went there, but it was cloudy all the time, so he didn't see anything there either. So that was a disappointment. So he went home with his tail between his legs, but worse was to come. Uh, he was delayed by storms and dysentery and blah, blah, blah. And when he eventually got back to France, he discovered he'd been assumed dead. He'd lost his wife, his title, and his estates, and uh, and most of his life, really. He did get some of that back, but anyway, so that was not a successful trip for Guillaume. This was a success in a completely different way. So somebody had to go to the far north of Norway, and it was a Hungarian gentleman who went there, John, how you pronounce that, um, and he discovered he started talking to some of the natives, and he could understand them more or less. That's a bit odd because he spoke Hungarian, and Hungarian was at the time believed to be a language related to no other language on earth. And he discovered essentially this language family. And these guys up here speak a language which is related to Hungarian, as do all these ones. That was fun. Nothing to do with the transit, though. Right, so the real story here is James Cook, um, an Englishman, of course. In fact, a Yorkshireman, son of a farm labourer. So presumably the local lord of the manor took to shine to this young lad and got him an education and got him involved in the seafaring. Anyway, he ended up as a naval captain, explorer, and all sorts, and an accomplished astronomer, as you had to be in those days, as we shall see, if you were to be a successful naval captain. And he was one of many, many people commissioned to go off and watch the transit of Venus in 1769. And he did that. Oh, and by the way, he also discovered Australia and New Zealand. Because after he'd visited Tahiti, he went on and discovered he had secret orders. So he got the orders to go and visit the transit. And he said, when you get there, when you've done that, open this envelope and it'll tell you what to do next. And it was to discover Australia, basically. So he did that. Right. Now, you'll notice here, he's traveling pretty much due west to hit Tahiti. And that's, of course, because in those days, um, Tahiti's longitude wasn't well known. So what you did to go to somewhere where you weren't quite sure of its longitude, you get the latitude right and sail west until you see it. So that's what he did. So he got there. He got there some months in advance because there's quite a lot of work to do before you could do this observation. And so he built himself a fort. Here it is. It's a picture by one of his men, presumably. Fort Venus on Tahiti. And there it is up here at the very northernmost point of Tahiti. Now, there's a reason it's at the most northern point, and that's important because the first thing you have to do, or first thing James Cook had to do, was establish the longitude, his longitude, actually. Now, I hadn't realized until relatively recently that, so the longitude problem, finding out your longitude at sea, was a famously unsolved problem until about this time. So this was about the time they began to get clocks that would work accurately at sea as well as on land, which enabled you to work out your longitude at sea. James Cook didn't have one of those chronometers on this voyage. He did on his subsequent ones. But it is possible to work out your longitude on land, at least you're there for a few months. And this is how you do it. So the first thing you have to do is observe sunrise and sunset a few times. So you're looking east and west. That's why you need to be at the northernmost point. So you can see the sun setting over the sea, both east to the east and to the west. And you get a very accurate timing. And that gives you local solar time. You have the equation of time available. so you can set your clock to local mean time. And you've got a clock that will work accurately on land. That's a big pendulum clock, grandfather clock sort of thing. So, and that can be pretty accurate. So, and you take that on ship, you wrap it up carefully on cotton wool or whatever, and unwrap it when you get there, set it up and regulate it. And then you've got very accurate version of time on land. And now what you do is observe an astronomical event whose time had been predicted. And James Cook observed eclipses of the moons of Jupiter from Fort Venus. Now, you may remember that in a previous video, Galileo had discovered the moons of Jupiter and said that you could use it to synchronize clocks. And that's precisely what James Cook did here. He also did it using what's called the lunar distance method, and I'll show you what that means. So he took with him yeah, sorry. So he established GMT to second accuracy to compare with local mean time, and therefore he knew his longitude. But it's the GMT thing that matters, actually. Right. So here is the Nautical almanac. It's not the one for 1769 that James Cook would have had with him. This is the one 2 years earlier, which is actually the first that were published in this form. And you'll notice that amongst many, many other things, this is quite a thick book, this. This has for every day of the year, this is January, it has, amongst other things, the eclipses of the satellites of Jupiter. So if you look at Jupiter with a telescope, you can see the moons, these Io, Europa, Ganymede, and Callisto, and you can see when they disappear because they're eclipsed. And these are the times when that was predicted. So then here is second, several years in advance, because this document, of course, would have been produced, I don't know, 3 or 4 years before it was needed. So that James could pack it in his locker and take it around the world and use it to work out where he was. So that's using the satellites of Jupiter. This is using the lunar distance model. So this tells you where the moon is relative to various stars at various dates. This is in December, actually, this page. So this tells you degrees, minutes, and seconds, how far the moon, the center of the moon is from Regulus. So if you to use this, you need to know your stars. You need to know which one's Regulus and measure how far away it is. So he used both those methods to establish his longitude and to establish GMT. Right, so now he is ready. Oh, here's his observatory, by the way. Well, I don't know whether it's really his, but it's one like it. I find it a bit hard to believe that he would have had an observatory stuck. It would have been in the fort, of course, but even so, I'd have thought he'd had proper walls rather than a flappy canvas wall, which would have made it more difficult to concentrate. Anyway, so this is what they paid all those millions of pounds to go get him around the world to do. This is his journal. It's worth reading this, actually. It's quite fun. Move this. So this is the transit of Venus, Saturday, June the 3rd, 1769. Time by the clock. That's interesting because in those days, time was usually measured by the sundial, not by clocks. But he's making it clear that he's using clock time. And the other interesting thing is actually that the Nautical Almanac, that gives time by the sun, interestingly, not time by the clock. So anyway, here we are. This is time by the clock. So it says here, it says hours, minutes, seconds. This is the morning. 9:21:50. That's 20 minutes past 9 in the morning and 50 seconds. First visible appearance of Venus on the sun's limb, very faint, as in figure 1. So that's the first contact, which is very hard to detect. And then, what's that, it's 18 minutes later or something. First internal contact. The outer limb of Venus seems to coincide with that of the sun and appeared as in figure 2. Now, there's a problem here, isn't there? And it's called the black drop. You get this sort of smudgy effect, which makes it actually rather hard to tell when this actually happens. So they have been hoping to get within a second, and they really didn't quite make that because of this awkward black drop effect. And so this is a minute later, and it's just escaped. It says small thread of light visible. So between here, so Somewhere between here and here is the first contact, is the second contact. It was pretty hard to tell exactly when. And that was the problem. So they didn't get quite as good a result as they'd hoped. Now, um, when Cook got back, they were the Royal Society, whoever it was who sponsored him, were very cross about this because he hadn't done what he'd been told. And in particular, they chose to blame his chief scientist, whose name escapes me at the moment, but who had unfortunately died on the journey back, so he wasn't able to defend himself. And James Cook was very cross with them about this. He wasn't having his scientist being the calumny of his scientist like this. And his rebuttal was so robust in his Yorkshire way that it was expunged from the record of the meeting. Anyway, it turned out everybody else had the same problem all around the world. Um, and in fact, you still do. That's what the 2004 transit of Venus looked like with a modern telescope. So it really is quite hard to tell that. And that's a combination of effects. At the time, nobody really knew what it was for. And I think even now, people are not entirely convinced they understand that phenomenon. But anyway, it did rather spoil the effect. But nevertheless, they got a good answer. So they used two methods to analyze the data. The exact time of second contact, that's when it's first fully inside the sun. You can only do that when GMT is known, of course, which James Cook did know, so that's all right. And alternatively, the interval between the second and third contact, which you can only do if both of them were visible. That is to say, if they're both in daylight. Because unlike most astronomy, this bit has to be done in daylight, of course. They both have to be in daylight, and it has to be not cloudy at both ends. Well, that was true for James Cook as well. So he did both methods. So a couple of years later, this Frenchman analysed all the data from both transits to arrive at a mean distance to the sun of that many gigameters. Um, Other people did other analyses. I mean, to be honest, the science of statistics had not yet been invented, and the statistical analysis here was more than a little suspect. But there we go. But nevertheless, it's not bad. That's the real answer. So that's pretty good, isn't it? So that is how we found how far away the sun is. So, in fact, of course, it varies, but they knew that, so they knew which one they were comparing against. Nowadays, it's much easier. You can bounce radar off Mars or Venus, or you can also triangulate using spacecraft in orbit around the sun. You can get very accurate, which means, with effect, we know the distance to the sun to within a meter or so. But actually, it's not quite clear what that means, is it? Because the sun hasn't really got a surface in quite the same way that the moon has. So, anyway, there we go. I hope you enjoyed that.